So, we will discuss about the crystal diffraction using X-ray. So, basically X-ray diffraction this from crystal. So, I have discussed about the source of X-ray, how X-ray is generated using X-ray tube, and also have discussed about the diffraction of visible light from grating. So, from grating, if you take diffraction, this is a grating and a set of parallel rays of visible light falling on this grating. It's perpendicular, these rays are perpendicular to the grating. So, then it is diffracted in different direction with say angle theta. So, this angle made with the normal to this grating. So, then we have seen that d sin theta equal to n lambda, that is the condition for principal maxima, means we have for this grating basically we have the diffraction pattern like this. So, this the intensity distribution of due to single slit effect, okay. And here then we get principal maxima, that is due to basically interference this equispaced maxima we get. This basically interference maxima, and this if I just remove this one, which is basically modulating the amplitude or intensity of this principal maxima, all are not having same intensity, So, intensity varies. So, this zeroth order, this is the first order, second order, third order. Okay. So, these are the value of n. So, we get basically, if I just we get just equispaced constructive interference having basically these are different peaks. Okay. So, these are due to interference of secondary wavelets. Okay. So, this is angle and this is the intensity. Okay. So, this is the grating element. So, this is middle of this and the next one. So, this distance is d, is called grating element. Okay. So, if we know lambda, then experimentally one can find out theta of different order angle, and then we can find out d, or if we know the d, then we can find out the lambda of unknown wavelength of light. Okay. So, one has to measure this angle experimentally, then one can find out either grating element or the wavelength of light. So, this in case of X-ray, as I mentioned, in case of X-ray, so wavelength is generally in the range of say 0.1 angstrom to say 10 angstrom. Okay. So, this using this X-ray, von Lau and Bragg WH Bragg and his son WL Bragg. So, they mentioned that X-ray diffraction also we can see if we get grating having this grating element of this dimension. Okay. So, in angstrom order grating element if we get, then we can see the diffraction effect of X-ray, but practically it is not possible to fabricate such type of grating. So, they actually mentioned that this is a good opportunity to study the crystalline materials using X-ray diffraction. So, in crystal, as I mentioned that this lattice spacing d value, lattice spacing for crystal, that lattice spacing it is in the range of say 1 to 5 angstrom. Okay. So, it is in the same range. So, one can choose appropriate wavelength of X-ray, and then that crystal planes a set of planes, parallel planes of crystal, it can behave like a grating having the spacing that is equivalent to the grating element, and we can see the diffraction of X-ray from the crystal. So, they propose that one, and also they have demonstrated the same, and they found the way to get the lattice structure, crystal structure, analyzing the X-ray diffraction from the crystal, right. So, for their contribution, so they were awarded Nobel Prize. So, von Lau, he received Nobel Prize in 1914. In 1914, it is, so he received Nobel Prize in 1914, and that Bragg, W. L. Bragg and W. H. Bragg, so they are basically father and son. So, Bragg received the Nobel Prize in next year 1915 for their, so independently they demonstrated the X-ray diffraction from the crystal, and using that X-ray diffraction from crystal they have demonstrated how to calculate the lattice parameters from this X-ray diffraction. So, because of this great contribution in crystallography, so they were awarded Nobel Prize. So, now we will see this whether similar type of relation in case of X-ray diffraction, whether that relation we can find out whether that type of relation is there or it's a different kind of formulation is required for X-ray diffraction. So, this so there are basically, as I told, this von Lau and this Bragg independently they found the way to study the X-ray diffraction and determination of the lattice constant of the crystal. So, they have given different mechanism treatment to for this X-ray diffraction. So, this so Bragg, so one is basically for X-ray diffraction, this we tell this Bragg's treatment, and another is Lau's treatment. So, basically this in different way they have shown the X-ray diffraction, and they have studied that X-ray diffraction for determination of the crystal structure. So, this Bragg treatment, it is basically it's based on model. but this Lau consideration, Lau's treatment is based on based on the X-ray scattering from each lattice point, from each atom in the crystal. So, these are more general treatment and more realistic treatment, but fortunately the result of this from these two both treatment results are same. For that one has to correlate both of the relation, but ultimately they are same. So, they give the same physics or same structure of the crystal. So, this based on basically based on X-ray scattering, from each atom in crystal. So, we will discuss both treatment, but let me discuss first this Bragg treatment, and this later on we will discuss about the Lau treatment, but from Bragg treatment itself whatever relation we will get, that is sufficient to study the crystal structure using the X-ray diffraction, and from Lau treatment it is general and more realistic, and from Lau relation whatever we will get from there, we can show that this from Lau relation one can derive the Bragg relation. So, let us discuss about the Bragg treatment. So, this Bragg treatment, as I mentioned, that it is based on the model. So, this what is the model? So, basically this they have considered, or it is true that this crystal a crystal have a set of planes, okay, and they have many orientation. Okay. So, there are many planes having different orientation, but as I mentioned that one crystal plane described by HKL, it is not a single plane, it is a set of parallel planes having the equidistant spacing. So, that is the basically lattice spacing, lattice spacing D, right. So, they consider that this in crystal let us take a set of parallel planes, So, So, we have considered a set of parallel planes. So, one planes means there is a this lattice points atoms on this plane, right. So, this one of the arrangement I am taking. So, all are same plane, HKL plane, say. Okay, so there are, I think, just you can take arrangement of the. Let us take the simple one. So this, I think I will not draw this one. So this is a set of parallel planes, HKL planes, right? HKL planes. So it is nothing but a set of parallel planes having the distance, spacing. So this is D, lattice spacing, so infinite number of these planes are there. So now if you so Bragg considered, basically, as I told, that he assumed assume that say crystal have a set of parallel planes with lattice spacing D, right, with lattice spacing D. Now, second assumption that they are telling that Xa, when Xa falls on this crystal, okay, so this Xa reflected from each plane, Xa reflected from each plane, okay, and for a, so if you take a, say Xa is falling, say one ray is falling here and it is reflected, right. So this is the perpendicular to this plane, perpendicular to this plane, okay. So this another beam is falling, another ray is falling. So beam of X is coming, so it has many rays, so it's falling on all crystal planes. So if I consider this second ray, so it's this is parallel rays. So yeah, it looks parallel. So this I have to make it parallel. Yeah, looks parallel. So, this is the normal to these planes, because they are parallel. So they are so they have same normal. Okay. So, now this X-ray, they are telling that X-ray beam will fall on these crystal planes. On crystal means it will fall on these planes. So, set of parallel planes, okay, and they will reflect from these planes. Okay. So, this ray is reflected following the reflection rule. So, what is that rule? So, incident angle will be equal to reflection angle. So, generally it is that angle is taken with respect to the normal. So, that is fine. So, one can take with the surface also, with the plane also. So, then we tell this the theta is the grazing angle, theta is the grazing angle, theta is a grazing angle, okay, angle with the plane. So, this here, since they are parallel, so here also this angle is theta, this angle is theta. Okay. Now, so these are so from third, fourth, fifth layers planes, this reflected ray will come following the reflection, and now they are telling that these reflected rays will interfere. Okay, there will be interference among these reflected rays, and it will give resultant will be the constructive interference from these reflected rays. Okay. So, when X-ray are falling, okay, so they will be reflected from these a set of parallel planes having the same index, okay, means lattice constant, same lattice constant. Okay. So, then these reflected rays will interfere constructively. So, there is no guarantee that this ray, when ray will interfere and you will get constructive interference, there may be destructive. It depends on what? It depends on path difference or phase difference. So, here it is fixed, that the difference is that here it is fixed, is it will reflect in such a way these reflected rays will interfere constructively. So, that is the assumption, that is the main assumption. Okay. So, it is that is why I told this is a model. So, if they consider this, so then what is the condition we will get? This interfere constant, so reflection. So, they consider the reflection from parallel planes, say HKL plane, so their lattice spacing is, so D, lattice spacing is D, lattice spacing D, right. So, now this reflected rays will interfere constructively, reflected rays will interfere constructively, that is the main assumption, interfere constructively. Okay. So, now when they will interfere, these two rays will interfere. So, this that path difference has to be for constructive interference. What will be the path difference? either path difference has to be equal to the lambda n lambda like this lambda integral multiple of that lambda, or this 2 pi integral multiple of 2 pi. Okay. So, then only they will interfere constantly. So, that is so they assume this from this model itself. So, this it is clear that this path difference has to be in lambda, okay, lambda, 2 lambda, 3 lambda, 4 lambda, etc. So, now what is the path difference we have to calculate from here. So, this is the d, this is the d. Now, how to calculate? So, just these are parallel. So, just draw a normal from here. Okay. So, path difference between ray 1 and ray 2. So, this path is same, this path is same for both rays, and only this ray 2 are travelling the additional path this and this, right. So, if this is the angle theta, so you can show that this angle, this will be the this angle theta. So, this will be also theta, this is the 90 degree. So, it will be theta, and this one will be also theta. So, this is d, if this is d and this is theta. So, this will be d sin theta, and this other one also will be d sin theta. So, this d sin theta plus this d sin theta. So, it will be 2 d sin theta, 2 d sin theta. Okay. So, this is the relation they established based on the model of reflection. Okay. So, this and it is difficult to tell why they consider the reflected rays and they will interfere constantly, but that was the assumption, that was the model, and got this relation, and this relation satisfy all experimental result. That means their assumption are correct. Okay. So, their model is correct. Okay. Later on we will find out that from Lau treatment, that is the rigorous treatment, general treatment, realistic treatment. From there we will get some relation, and from that relation one can derive this relation. Okay. So, this is the simplest way. Bragg's law is very famous because of its simplicity, and using this relation we can study the crystal, we can find out the crystal structure. So, that we will discuss in next class. Thank you. I will stop here.